number 1. Hayden. That's fine. Explain your way. Because I was going to explain your way the next one. Because I like your way. Go.
Both 45s, they equal to 1. And then the hypotenuse is root 2. So I just take the 4 from the root 2. Like 4 times root 2. And I just put it where
Yeah.
x is.
Very good. So Hayden's saying if this is 45, 45, 90, this has to be a times the square root of 2. In other words, whatever this side length is times the square root of 2. Do you guys agree? And this is 4 times the square root of 2. So a clearly has to be 4, right? So that means x is equal to 4 over here and x is equal to 4 over here. Very good. Okay? No? Diana, how would you explain it differently?
So we know it's 45, 45, and 90. So it would be x 4 to the square root of 2.
Uh-huh.
Because like, how I did it was I put 45, 45, 90 first, so that way I could place it.
Yep.
And then I put x under 45, x under 45, and 4 square root of 2 under 90.
Okay.
And you know that that's a square root of 2 times a.
Mm-hmm.
You know that those x's are equal to a.
Yep, x's are going to be equal to a's. 4 times the square root of 2 is going to be equal to a times the square root of 2.
Yeah, 4 to the square root of 2 equals the square root of 2 times a.
Mm-hmm.
You divide the square root of 2 by both sides. You see the square root of 2 cancels out on both sides, so that a equals 4.
And if a is 4, then x is 4. Very good. Okay? So what Hayden, I actually really love how Hayden's doing it. So if you're like really not getting these problems, okay, I want to show you Hayden's way because it's very, very helpful, okay? You probably want to write this down on that second slide of the warm-up. Write down 45, 45, and 90. What Hayden does is he compares them as a ratio, right? So the legs are going to be 1. And it's 1-to-1 ratio because both of the legs are the same length because it is an isosceles triangle. But the hypotenuse, the side across from the 90, is related to the legs how? Not 2. The square root of 2 times whatever value that they are. So if the legs were each 1, then that hypotenuse would be the square root of 2. Okay? He does the same thing for 30, 60, 90. So for 30, 60, and 90, he starts with the smallest leg across from the 30 being a unit of 1. Then the 60 would be what ratio? The square root of 3. And then the hypotenuse across from the 90 would be what? Not square root of 2. 2. 2 times 1. Okay? So remember, the hypotenuse in a 30, 60, 90 is always double the length of the smallest leg. And the longer leg is always the square root of 3 times as large as the smaller leg. Okay? All right, in this second one, okay, it gave you one of the legs. It gave you that the leg was 3. So how do you then find the hypotenuse if the leg of a 45, 45, 90 is 3? What do you do? Hayden? You just do 3 times the square root of 2. Okay? Remember, the hypotenuse for a 45, 45, 90, let's write it out, 45, 45, and 90. If one of the legs is 3, then the 90 is going to be a times the square root of 3. Oh, excuse me, 2. Square root of 2. And we know that a is 3, so it's going to be 3 times the square root of 2, which gives you 4.2. Dealing with is similar right triangles in today's lesson. Chapter 9, section 3. Theorem 9.6, okay? In this theorem, the good news is you don't need to know the name of the theorem, right? It's just theorem 9.6. But you do need to know how to apply it. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle, and they're similar to each other. So what you really need to know for this guy is that there are three similar triangles. There's that original one, the entire green one, right? The whole thing. There's that smaller triangle on the left, and there's that medium-sized triangle on the right. Now, your job is going to be to identify what the three triangles are and figure out which angles and which sides are corresponding, okay? And I have a way of doing this, and it involves a shorter leg, a longer leg, and a hypotenuse, okay? So I want you guys to zoom in on the left-hand side of the triangle. So in other words, ACD. Which of those three sides is your hypotenuse? AC. So put an H there. And take a look at which one would be your shorter leg? CD, so put SL. And which one would be your longer leg? AD. Now, I want you to look at ADB. ADB. What is your hypotenuse? AB. What is your shorter leg? AD. And what is your longer leg? So hold on. Do you see how AD is being used both as a longer leg and a shorter leg, depending on which triangle you look at? Interesting, right? We will get into why that happens in a little bit later. And then the last one, what's the last triangle that I haven't talked about? The massive one, right? The whole thing. What's the hypotenuse of the entire largest triangle? AB is not the hypotenuse. CB is the hypotenuse, okay? Do you guys see that? What's the longer leg for the whole hypotenuse, for the whole triangle? AB is going to be the longer leg. And what's the shorter leg? AC. So do you guys see there's like definitely some overlap here, right? And if you were to try to write a proportionality statement, a similarity statement right now, it could be very difficult. Do you guys agree? Because a lot, like the letters are being reused, they're overlapping, it gets really difficult. What do you think we could do to help us out when we're writing a similarity statement between these three triangles? Yeah? Yeah, just redraw them, right? So what we're going to do for these types of examples is we're going to redraw it using three different triangles, okay? So I want you guys to move on. I don't really like this picture that much. Let's move on to this one, okay? So go to example 1. Skip that second slide. We'll go back to it, okay? But what I want us to do, and I always, you don't have to do it this way, okay? But I always set it up the same way so I have a template. And I always set it up as all three triangles are going to be the same orientation. They're going to have shorter leg on the left, the longer leg will be the base, and the hypotenuse will be over here, kind of like slanted on the right-hand side. That means my 90 goes right here. And now, as long as I line up each of those triangles the same way, I can tell very easily what letters and what angles are going to be corresponding, okay? So let's check it out. Let's first take the largest triangle. What are the three letters for the largest triangle? STR. So let's go ahead and let's outline it in red. Remember, I don't want it oriented like this. I want it changed so the shorter leg is on the left, the longer leg is on the bottom, and the hypotenuse is over there slanted to the right. So I'm going to draw my triangle. What goes at the 90? What letter goes at the 90? T. Do you see how in your figure, the 90 degrees for that big triangle occurred at the T? So that T has to go down there. What letter would go above the T? S. And what letter would go to the right? R. Congratulations, you just did one of the 3 triangles. Let's do it again. So, what's another triangle we can do this for? UTR. I like it. So outline it. Use a different color. Outline it. All right, let's draw the same figure with our 90. What letter goes at the 90 position in UTR? U. Very good. What letter should go above U? Remember, that's part of the smaller leg. Very good. T. And the last letter? R. So guys, double check. Is UR your longer leg? Is UR your longer leg? Bingo. Okay. So if you look at UR, do you see how it's much longer than UT is? That should match your diagram. So now look at these 2 triangles. Isn't it very easy between the red and the blue one to identify what the corresponding parts are? What's corresponding to S? T. What's corresponding to T? U. What's corresponding to R? What's corresponding to R? R. So does that kind of make sense? So let's do it again, but for the last triangle. U, S, and T. All right. Let's go ahead and draw our picture. Shorter leg on the left, longer leg on the bottom, hypotenuse. Where's my 90? What letter goes there? Very good, it's U. What goes on top of it? S. And to the right? T. So now, guys, part of what you're going to be asked to do is write a similarity statement. And in these similarity statements, the order 1000% matters. So someone take a shot, now that we've drawn all 3 of our triangles, at writing the similarity statement between the 3. Kristen?
Triangle STR is congruent to triangle TUR, which is congruent to triangle SUT.
Very good. The only thing I would change, Kristen, is I would not say congruent. These are all similar, okay? And you said SUT?
Yes.
Very good. All right, I'm going to challenge you guys. Someone else come up with, also it needs to be an accurate similarity statement, but with the order it needs to be different. Go ahead, Christian.
Triangle TUS is similar to RUT, and that one is similar to RTS.
Is Christian right? I agree with him, okay? He did reverse the order. So do you see how the green triangle, his green triangle came first, okay? So he did the green triangle first, and he reversed the entire order. So he went, instead of first to last, he went last to first. But he did that for all 3 of them. So it went RUT instead of TUR. And then he also, instead of STR, he went RTS. So he is absolutely correct as well. Very good, Christian. Anyone want to try? One more person want to try? Nick, go for it.
Triangle TRS is similar to RT, which is similar to UTS.
You said RTU?
Yeah, wait.
And you said similar to, what was the last one? What was the last one you said, Nick?
Because I forget the other one.
UTS. Okay, so this is good. I'm glad that you made a mistake. Now let's identify it. Does anyone notice where the mistake was in Nick's? Alexis?
RTU.
Very good. It's in the middle one. Very good. What does it need to be instead of RTU, Alexis?
URT.
Very good. It needs to be URT. Hey, I'm glad we made a mistake because that's a learning opportunity for us, okay? It's all right, Nick, okay? That's why we practice this. And I'm glad that you took a leap of faith and you tried your own, okay? You figured it out last minute?
Because when I was doing the last one, I said it wrong way.
So, are we good now? We understand that the order matters? Does it help to draw out the triangles? Some of you are like, you get it conceptually, you can do it in your head, okay? I recommend if it's not like completely natural for you, draw out the triangles so you can see it, okay? All right. Next thing we're going to talk about is something called a geometric mean, okay? And all I want you to focus on is don't look down at anything. I want you to focus on this. Let's say we had A and B were numbers, right? And I asked you to solve for X. What would you do to solve for X here? Cross multiply. So let's go ahead and cross multiply. We would do X times X. What's X times X, guys? X squared, not 2X. How do you get 2X? X plus X, right? So X times X is going to give me X squared. What do I do next? A times B, right? What is A times B? There's A times B, right? All right, and we're still solving for X, correct? What would you do to solve for X? Take the square root of both sides. What happens when you square root something that's squared? What happens when you square root something that's squared? Cancels. So we have X equals the square root of A times B. This is geometric mean, okay? So a question may ask, what is the geometric mean of A and B? You will multiply those two numbers and then take the square root of your answer. Okay, so why is this important? When we are setting up our proportions for these problems, guys, what's going to happen is we're going to find that the geometric mean is going to happen because do you remember when we were drawing those pictures of the three triangles? And I said, oh, longer leg is being used as shorter leg as well. You're going to have variables that are going to line up across from each other in a proportion, and they're going to get X squared, okay? Or whatever you're looking for squared. So that's why this is going to happen. That's why geometric mean is so important. Okay, so how do we use geometric mean? Let's first find the geometric mean of the given numbers. Go ahead, Kristen. So we have 4 and 20. So we'll say X is going to be equal to, what do I do with those two values? So let's think of 4 and 20 as our A and our B values. You multiply them, so let's do 4 times 20. But we also had to do something else to them. Take the square root of that. So it's going to be the square root of 4 times 20. What is 4 times 20, guys?
80.
So X equals the square root of 80. Use those calculators. What is the square root of 80? It's 8.9. Okay? What would I do for the second one? For 9 and 25? X equals?
225.
The square root of 9 times 25, which is the square root of 225. So X equals the square root of 225. Plug it into your calculator. What's the square root of 225? X equals 15. So are we all okay on what a geometric mean is? It's going to give you two numbers. You multiply those two numbers, and then you take the square root. Understood? Any questions on geometric mean? Now, how does this apply to what we just learned about? That's on the next slide, okay? So the theorem 9.7, aka the geometric mean altitude theorem. In a right triangle, the altitude from the right angle down to the hypotenuse divides the hypotenuse into two segments, segment 1 and segment 2. The length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. Basically, when you set up a proportion for these two right triangles, the right triangle on the left and the right triangle on the right, if you're comparing the legs, it would be segment 1, which is the shorter leg, over the altitude, because that's also the shorter leg of the triangle on the right. And that would be proportional to the altitude, which is the longer leg of the triangle on the left, over segment 2, which is the longer leg of the triangle on the right. And this gives us a geometric mean of segment 1 and segment 2. And just for our sake, we'll label it A and B, right? So segment 1 is going to be A, segment 2 is going to be B. So this will be the geometric mean of A and B. So we're going to do 2 examples with this on this slide, okay? Okay, the first example I want to do, actually guys, can you guys add a slide below? Because I want us to have a little bit of space, okay? So the first example we're going to do is we're going to draw a right triangle. And we're going to draw its altitude down from the top. So we know that this is 90 and this is 90. We'll make the altitude x. We'll make this piece 3 and this piece 7. So what this theorem says is when you set up a proportion, right, you're going to end up getting x over 3 equal to 7 over x. X over 3 equal to 7 over x. And what we do is it's basically just going to turn into the geometric mean of 3 and 7. So let's write that down. Geometric mean of 3 and 7. Now, we just did this on the previous slide. How would I find the geometric mean of 3 and 7? Go ahead. Multiply and then take the square root. So x is going to be the square root of 3 times 7. What is 3 times 7, guys? 21. Take the square root of that. And I believe I got 4.6. Can you guys check me on that? So it's the square root of 21, which is 4.6. Okay, now, what would happen if we weren't given like the 3 or the 7? What if we knew what x was, but 3 or 7 was missing? That's a separate example. So let's go ahead and take a look at that example. I want you to draw this very similar picture, okay? With the altitude, the 90 over here. Let's say we didn't know this. We knew that this was, let's make it 8, and this was, I don't know, 6. So remember, 6 is now the geometric mean of x and 8. 6 is now the geometric mean of x and 8. Nick, do you think you know how to set it up? Excellent. But let's set it up in a formula so we can remember that. So remember, x was equal to the square root of 3 times 7, correct? But instead of x, now I have 6, right? So 6 is going to be equal to what? The square root of x times 8. So now what we're solving for is now underneath the radical. And Nick was correct. The first step to solve this is to do what? Square both sides. So when you square both sides, what happens when a square root is squared? cancels out. What's 6 squared? So we have 36 equals x times 8. And the last step? Divide by 8 on both sides. What's 36 divided by 8? 4.5. So 4.5 equals x. Okay, we are going to learn 2 more applications of the geometric mean tomorrow, but for now I need you guys to turn these in. This will be part 1 of your notes. Your homework is going to be due on Thursday because we have not finished the lesson. Hey, that does not mean save everything for tomorrow night. You can at least do half the homework at this point, okay? There's only one more set of examples we haven't looked at yet, okay? The next one I want you guys to do, this will be considered your warm-up. Now it is going to be reversed, so it's going to be upside down, okay? But let's say we don't know the altitude. This piece is 4 and this piece is 9. Go ahead and try to find the value of x. Geometric mean, this x is going to be the geometric mean of 4 and 9, okay? So we're going to say x is equal to, what does the geometric mean mean? Mean? What is a geometric mean? What do we do with those two numbers? You take the square root of their product. What does product mean? What does the answer mean? What do we do with them? Operations, people. You multiply them. 4 times 9. What is 4 times 9, people? So what's the square root of 36? So the answer to x was 6. Yeah, give me 2 seconds. Thank you. How'd we do? Gucci? All right. Let's pause for a second. We're going to finish these notes today. The thing that we're learning about today in 9.3 is the geometric mean theorem when you're not talking about the altitude, okay? In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Guys, what does adjacent mean? Next to. Write that down. So in our previous examples, right, we were talking about the altitude. So we didn't know what the altitude was, and the altitude became the geometric mean of the length A and the length B. Do you guys remember that? Now what we're talking about is we're talking about x, which is that leg on the left, or y, which is that leg on the right. So x's value is going to come from the geometric mean. It's going to be the geo mean of the adjacent portion of the hypotenuse. So look at A and look at B. Which of those 2 values is next to x? A. So it's the geo mean of A and the entire hypotenuse on the bottom. What's the length of the whole hypotenuse on the bottom? C. A and C, okay? Now, when we're looking at y, we follow the same steps. So y is going to be the geo mean. Now, which segment of the hypotenuse, which piece, is adjacent to y? B, very good. So it's going to be B, and then again, we use the whole thing on the bottom. What was the whole thing on the bottom? B and C, okay? Now, this is different than that one down the middle. Do you guys see the black one that I circled? The black circle around that segment? That segment, that altitude, was the geometric mean of what 2 values before? A and B, okay? We are not using A and B together now. We're using A and C or B and C, depending on which side we want, okay? So let's go ahead and try some practice with this. Let's say we know what JR are and EJ are. Let's find HJ, RE, RH, and HE, okay? Really quickly though, guys, please duplicate this slide because we're gonna do A on this one and we're gonna do B, but we're gonna have to change the numbers in our diagram, so I want you to have 2 copies of this. Do you know how to duplicate a slide? Help your neighbor if they don't. You click like the pages button on the right, and you click the 3 dots on the slide that you want to duplicate, and there should be a duplicate button. Oh, you just copy and paste it? Oh, sorry. There's no duplicate anymore? There used to be. Oh, just click copy and then paste it. I'll give you guys another second to figure that out. We're good? Okay, so it says JR is how long? 16. Where's JR? It's bottom right, right? So let's put a 16 there. Where's EJ? 9, and it's on the left. Okay. All right, so how would we find, let's go ahead and do HJ. How would we find HJ? Cody? Very good. HJ, write this down, is the geomean, the geometric mean of the 9 and the 16. So just like Cody said, right? HJ is this value. You can make it x, right? So x is going to be the square root of 9 times 16. Now, we have calculators for a reason. Go ahead and plug into your calculator 9 times 16. What do you get?
12.
It's the square root of 144. I don't know where you got 12 from. Just kidding. The square root of 144 is 12. There you go. Is it working now? Let's go ahead and find RE. Where's RE? It's on the bottom.
9 plus 16.
Ooh, just add 9 plus 16. So RE is going to be 9 plus 16. What's 9 plus 16? 25, baby. Easy, right? Okay. So we're moving on. Where's RH? Where is RH? It's what? Top right, right? So it's going to be, let's make this Y. So RH, remember now, use the previous slide. It's going to be the geomean of what 2 values? RJ and RE. Guys, it's going to be the geomean of this 16 and then the full length on the bottom, which is 25. You guys with me or no?
No.
Okay. So remember, if you're looking for, let me zoom in here. If you're looking for this value down the middle from H to J, right? You take the geomean of this 9 and this 16, both separate segments, right? If you're looking for this piece on the right, what's the piece that's next to Y? 16 and the whole thing, which is 25. So we're taking the geometric mean of 16 and 25. Okay? So, what does it mean to take the geo mean?
X squared 6 times 16 times 25.
The square root of 16 times 25. Very good. Okay? Remember, we used x already, John, so I'm just going to leave it as y. Okay? So we're going to say y is now equal to, what do we get there, guys? You should get the square root of 400, which is 20. Very good. Okay, so we're almost done. We have one more piece to figure out. Ah, very good, Dylan. So the last piece is that leg on the left side, EH, okay? And EH, we're going to label it Z, right? Or HE. And Z or HE is the geo mean. And just like Dylan said, it's going to be the geo mean of 9 and 25. because it's the adjacent segment, which is the 9 piece, and the whole thing, which is 25. So we're going to say, okay, z is equal to the square root of 9 times 25. And I believe you get z equals the square root of 225, which is 15. And we found all 4 of our values. You guys all duplicated this slide, correct? Okay, awesome. So on your second slide, I'm going to erase everything. On your second slide, let's go ahead and start doing B. Can I erase? Okay. So in B, it says JR is equal to 4. So let's go ahead and fill in a 4 there. And it says JH is equal to 2. Let's first find EJ. We'll make it X. All right, now let's think about this one. What do you think we could set up to solve for X? Not plus, times. That is correct. So we're going to set it up, guys. Do you guys agree that HJ is the geometric mean of X and 4? And we know what HJ is, so we're going to set it up as 2 is equal to the square root of X times 4. Yeah, go ahead. So, really quickly, guys, how would you go about solving for X here? Diana? Not square root the both of them. Square both sides. Very good. Because what happens when you square a square root? They're going to cancel. Very good. Because they're inverses of each other. So what's 2 squared?
4.
So we have 4 equals, what's X times 4? How can I rewrite that? Just 4X. What do I do next? Divide by 4. And what's 4 divided by 4? X is equal to 1. So X is equal to 1. How do we feel? So X was no longer that altitude, right? You could be given the altitude in another segment, and you could be asked to find the other piece of that hypotenuse, okay? So X is equal to 1. Does anyone know what RE is then? Very good. How'd you get 5, Dylan? Very good. 4 plus 1 gives me 5. So the length at the bottom of the hypotenuse, the whole thing, is going to be 5. RH. Any takers? John. Ah, very good. The geometric mean of 4 and 5. So we're going to say that RH is the square root of 4 times 5. What is 4 times 5, peeps? It's the square root of 20. Go ahead and take out your calculators. Type in the square root of 20. Do it now so we all can confirm we're getting the same result. 4.4? 20. Let's take the square root of 20. I got 4.5 when you round it, because it's 4.47, so it should round up. So where did I put that? Oh, RH equals 4.5. We have one more. What was the last length? HE. All right, HE is going to be the geometric mean of what 2 values? 1 and 5. That means we're going to be the square root of 1 times 5. What's 1 times 5? 5. What's the square root of 5? Do you know it off the top of your head? I don't. So let's plug it into our calculators. The square root of 5 is 2.2. And that's it. How are we feeling? Are we okay? Really good? Love it. Okay. Hey, now, what would happen, guys, if the triangle was flipped upside down? Would we freak out? No. It helps sometimes just to redraw it. Just be like, okay, I'm going to copy all the same numbers, and I'm going to draw it the way that I want it, okay? And I'm going to redraw it upside down, okay? All right, let's take a look at another example. So let's take a look at this example. A roof has a cross section that is a right triangle. The diagram shows the approximate dimensions of this cross section. Find the height of the roof. So we're looking for the value h. So h, remember, is going to be the geometric mean of RW and WT. Do you guys agree? We don't know what each segment is, okay? But we know that the whole thing is 65 feet, correct? How could we figure out what RW and WT are? Juliet? Very good. Let's start with ST. We know that ST is 60. So 60 should be the geometric mean of what two values? WT and RT. We know RT is what? 65. So let's put a 65 in here. And let's say WT, let's make it X, right? So you guys agree that 60 should be X times 65 and take the square root of it? You guys with me? Are you sure? Who said no? Okay, where did I lose you?
I never caught on.
Okay, so this 60, right, is on the right side of my triangle. It's going to be the geometric mean of the segment of the hypotenuse that's next to it, which is WT. We're going to make that X because we don't know its value, okay? And the other value will be the whole length of the hypotenuse on the bottom, which is 65. So we take X times 65, we're taking the square root of it, and that should be equal to 60.
Why aren't we doing like 25?
You could also do, guys, what would it be to set up for 25? 25 equals the square root. Let's pick a different variable. Let's say it's y over here. Y times what? 65, okay? Okay, so let's go ahead and start on this one in red, because that's the one that we picked in the beginning. How do we solve for x, guys? Square both sides, very good. What's 60 squared? 3,600. What happens when you square a square root? They're inverses, they cancel. So what do I have on the right? 65x. What do I do next? Divide by 65, divide by 65. What is 3,600 divided by 65? 55.4. Hey, do we have to use geometric means to solve for y? Does anyone know a little bit of a faster method? Nick? Very good. Subtract 55 from 65, or 55.4 from 65, right? Because if the whole length is 65, do you agree that if we just subtracted the piece that we found, we would get the missing piece? So do 55.4 and subtract that from 65. And you'll get that other piece is how long? 9.6. So we have 9.6 and 55.4. How do I solve for h now? Juliet? Very good. 55.4 times 9.6. Because it's going to be the geometric means of both those segments on the bottom. So we would say h equals, let's do 55.4 times 9.6. Let's see what we get. 55.4 times 9.6. You should get like 531.84 and then take the square root of that. 23.1? 23.1. What units? What units? What? Feet. Questions?
I got lost.
Where did I get the what? FE. Oh, the feet? That's just the units. That's a T, my bad. Yeah, Diana.
Why does it be sulfur nitrogen?
Okay, so Diana, do you agree that the whole length on the bottom is 65?
Yes.
We found 55.4. How do you find a missing piece if you know part of it and the whole thing? Don't divide. Just subtract. What's 65 minus 55.4? And that gives you 9.6.
Then why do you have the equation over there?
We could have used that as well, and you would get 9.6 as well. Try it. I can almost bet you're gonna get the same thing. Okay? You got it? You got there? Okay. Any other questions? All right, the last two examples I want you guys to try completely on your own, and then we'll go over them at the end. Just two. There's just two left. So the first one was 4.2 equals x. The second one was y equals. Should have been 7 times 2, which is 14. Take the square root of 14. 3.7. I want you to talk about it in your group, see if you guys can figure it out, and then turn these in when you got it. Go. A few people ask me about B, so let's go over it. Guys, B is one of the ones where it's not facing the same way. Do you guys see that? The full hypotenuse, do you see, is like over here? So I would recommend, if it's confusing you, to just redraw it, right? So I'm going to redraw it. My 90 is over here. My altitude's right here. I have a 2 over here, a 5 over here, and a y. I just shifted it, right? I turned it. So the hypotenuse of the whole triangle, the big triangle, is on the bottom. So y, right, is going to be the geometric mean of what? Not 2 and 5. 2 and 7. It's going to be the geometric mean of 2 times 7. Where's 7 coming from? Adding 5 and 2. That's how we get 7. And 2 times 7 is going to give me y equals the square root of 14. So y equals 3.7.
So why couldn't you use 5?
Because 5 is the piece. Is 5 touching y? No. You have to pick the piece that's adjacent to y. Okay? We use the 5 when we're calculating the length of the whole hypotenuse on the bottom. And that's where we got 7 from. Okay?